Hi, the end is in sight, right? We are in chapter 10. This is our last chapter. I think we'll just do a few sections, do a little review, be done. Yeah, chapter 10. Chapter 10 is a bit of a repeat, but brings up some interesting ways to do problems that I don't always think of them. I don't know. I always think in terms of fitting a density function and working with that, but there's lots of ways to solve problems, and I have a page of some that are done in 10.1 that I think are kind of fun and interesting. Different. I wouldn't solve them the way the book suggests, but they're good options. So I thought I would show you that because the rules in chapter 10 we already really did already. Um, and then 10.2 is new. It's on covariance, which is the variance between two random variables. So, I don't know, it's kind of nice just a follow up. I always put 11 first because I feel like in chapter 11 you need to see moment generating functions to be able to understand how to sum random variables. So that to me is more important than 10, and I'm kind of going backwards to catch 10 now. So I know you're tired, I'm tired, so we'll do the best we can to get through a few more sections and then call it the end of the summer. This has been I've enjoyed it. It's been a little bit longer than I thought. I didn't realize it would go the whole summer. So anyway, just okay talking. Here is a start time with a comic. This I got from Dr. Holder. I think it's kind of fun. So we should color, or we should get to lecture, right? That's probably better, but we'll just put like a little red in there. A little red in their mouths. Give them a little bit of hair, right? Dancing crazy girl. Okay, anyway, let's move on. So 10.1 is about expected values and sums of random variables and variances. And, I feel like we've already hit this in several chapters, so let me just remind you of a few theorems. Let's see, if I have random variables x1, x2, xn, so these are all independent. Well, they don't even have to be independent. They don't even have to have the same distribution. These are just n random variables. And if I want to find the expected value of their sum, where in fact I might even have a constant in front of the random variables, that's just the sum of their expected values. So maybe it's nice to give an example here that might help. So let's turn the pen on. Let's do a totally new color. Let's do purple. Okay, so let's just say you want to find the expected value of 2x plus 3y, where x and y are some random variables, have certain means. This is going to be 2 times the expected value of x plus 3 times the expected value of y. And yeah, I just need to know that these are random variables. They don't even need to be independent. And then these are these constants alpha that are up in this problem here. So that's just a nice example of theorem 10.1. If in addition I have independence, then the variance of the sum is the sum of the variances. And notice here, I think I even had this as a bonus if you proved it earlier, maybe back in chapter 3 or something like that. The constant here actually comes out squared because remember in the formula for variance you have f of x times x minus mu squared. So it's not surprising if you had a constant in there that's going to come out squared in your eventual formula. So if you have the variance of a sum of a bunch of random variables, that's going to be the sum of their variances as long as you have independence. That's the big one. And notice that the constants come out front squared. So let's look at the variance of 2x plus 3y. That would be 4 times the variance of x plus 9 times the variance of y. Okay, so that's just another example. And we already have done this in chapter 10, well 11. If I have a bunch of independent normal random variables, So again, I'm gonna, I should say if xi is normal, well, I don't have to say IID because I said they're all normal. But I should throw in here, definitely they need to be independent to add variances. So assume xi are a bunch of normals with the same distribution, but they're independent random variables, so one doesn't affect the other. Then the sum of the xi is a normal distribution. So sum of normals is normal. I add their means, I add their variances, and then to get the standard deviation, I take square root of the sum of the variances. So, I don't know, do I need to, I mean, we've done this in the last several chapters, so I'm allowed to add means, I'm allowed to add variances. You're not allowed to add standard deviations. That would mean, I mean, you can't separate this and take square roots of pieces. You're not allowed to say this plus this plus this, so be careful. I can add up all my variances and then take square root to get the standard deviation. So, in the central limit theorem chapter, when we were looking at the distribution of x bar is just the sum of n random variables divided by n. And again, as long as I have independence between those random variables, yeah, I mean, all over here I should have, again, that the xi are independent. If each xi is an independent. Okay, so notice expected value of x bar, I can pull out 1 over n, because we said if you have a constant you can pull out a front, just the sum of the expected values. So 1 over n, all of these are mu. 1 over n, that's n mu's, so this is mu. So when you add a bunch of random variables, right, the distribution of x bar is going to be normal. The mean will stay the same, and the standard deviation, remember, got smaller. So standard deviation is sigma divided by square root of n, because this is the variance. So with variance, again, if these are independent, the constant comes out front squared, and then I can take the variance of the sum, which is the sum of these variances. There's n of them, so 1 over n squared times n sigma squared, and then there's the standard deviation. So that's nice. Sum of normals is normal. If I average a bunch of normals, I get normal. The mean stays at the mean. The standard deviation gets smaller. So here's an example. I guess I already did it. Suppose IQ students are normal with a mean of 110, standard deviation of 16. What's the probability that I take 10 students and I average their IQs? So imagine x bar is, I'm just going to make up, like maybe one student is 101, 120, I don't know, 99 divided by, this is 10. So again, imagine I take 10 students. Individually, this is for any one student what the mean and standard deviation is. So if I take 10 students and average their mean and standard deviation, this is a graph of x bar. The mean, I mean, if the mean of one of them is 110, then the mean of the average of 10 of them should still be 110. And this is the distribution of x bar, so the standard deviation should shrink up, right? So this is 16 divided by square root of 10. Okay, so that is x, that's what I'm saying right here, actually. I already have it written. X bar is normal. There's the mean, there's the standard deviation. So what's the probability I took 10 students and x bar for those 10 students is bigger than 112? So again, this is a random variable, right? Because every set of 10 students we take, we're going to get a different x bar. So this is the graph of all the x bars. What's the probability those students, certain students, are 112 or more? So again, I imagine it's in that part of the tail. So this, you can see right here, I'm just using, I'm going to use Maple and do an integration. 1 over square root of 2 pi times, here's sigma, x minus mu 2 sigma squared, or z squared, right? So before, what we've been doing, I take x bar, subtract off its mean, divide by standard deviation. So here's 112, subtract off mean, divide by standard deviation. I get a number, I go to my z table. So yeah, I'm getting a little bit long. So I'm going to do some, I think some down here, some fun examples of using expected values to answer questions. I would have done these problems differently. I'll probably show you that and then show you the way the book does it. I mean, it's just playing around with expected value. It's kind of some nice little problems.